because I have no idea what's going to be open tomorrow or not.
I can tell you, nothing will be open tomorrow.
And second, there will be fewer trains. So try to leave a bit earlier from the hotel.
Do you need a recap? Was yesterday too long ago? So what was what were we talking about? So our picture of the universe is, as we see from observations and the story that we tell ourselves right now, is that it underwent this accelerated expansion, which flattens the universe, makes it very flat, very homogeneous. But quantum mechanically, this expansion is not exactly the same everywhere. There are small mismatches in the history of expansion, of accelerated expansion. And this is responsible for the perturbations that we see in the sky, like the clustering of radiation and matter at large scales. Okay? Inflation is a simple, effective description of this, where we have a scalar field that we don't know what its microscopic origin is, and we usually think of it as having some potential energy, and if its expectation value is up the hill here, then it effectively gives you a cosmological constant. So this error is well approximated by de Sitter space, but the dynamics of the scalar field is such that it rolls, and eventually this period stops. Otherwise, it's too much of a good thing, if inflation lasts forever. And then when it gets down here, it oscillates and heats up the universe, and we land into the warm, hot Big Bang phase of the universe. And this is very interesting, very nice. This is very hard to probe. And inflation, what really leaves phenomenological observational teeth, is in this period here. Okay, so this is inflation, and this is reheating. Okay. We defined yesterday what inflation really means. You can write the equations of motion for this system. There is an energy balance equation, also known as the Friedmann equation, controlled by the potential and the kinetic energy of the scalar. We use this slow roll approximation, not necessary but convenient, of neglecting the kinetic term. But the kinetic term, though small, is not zero. So very slowly, the scalar drifts down. And at some point, if in one Hubble time, the Hubble parameter changes at order 1, then we know inflation stopped. So the formula we write to express this thought is that you define some dimensionless quantity, which is the change. Of course, there's a minus sign because the Hubble parameter is always decreasing. So in one Hubble time, you want the Hubble scale to not change by order 1. So then when it changes by order 1, we declare that this is the end of inflation. Okay? And for our practical purposes, for the scales that we observe in the CMB, which are not all the scales of inflation, the CMB really probes some slice of this period, some number of Hubble times. And for our practical purposes, we're going to assume that within this slice here, epsilon is much smaller than 1. So when epsilon goes to 0, the Hubble parameter doesn't change at all, and we fall back into the Sitter space, which is beautiful, symmetric, lots of structure. So we're going to use some de Sitter approximation and mildly break it with this epsilon. We'll see that it is essential that epsilon is not 0. You'll see it in a couple minutes. So we described the background, and then on top of this background there are fluctuations. So the simplest model of inflation is this single field slow roll. Action is very simple. So this is the action. And so it has 3 degrees of freedom, right? I was having a little chat with Tarek yesterday. Constraints, what is it? Constraints strike twice, right? So everyone remembers why GR has 2 degrees of freedom, even though the metric has 10 components. So what is the equation? So there are 2 degrees of freedom from here, and 1 from here. I guess this 1 degree of freedom everyone is happy to accept. And 2, so it's a famous equation in physics, 2 is 10 minus 4 minus 4. Okay. So where does the minus 4 come from? That's 1 minus 4. Where is the second minus 4 coming from? That's the same minus 4. Where's the second minus 4 coming from? I think they're the same minus 4. Let's go back to, let's do, yeah, sorry, this is a parenthesis, but this is for your general education. So it's a public service. So 2 equals 4 minus 1 minus 1. This is an important equation. So if I take a vector, a gauge field, A mu, it has a gauge symmetry, right? A mu. So this one, everyone knows. So that's this minus 1 here. Where about this one? Not gauge, not gauge, not gauge. No. Okay. Well, what's special about this kinetic term here? Why don't you just write the mu a nu squared? Okay. Let's start. 3 equals 4 minus 1. Okay. So let's do proca. No gauge symmetry. Okay. The kinetic term is still F mu nu squared. Don't tell me Higgs mechanism, okay? So this is a completely fine theory on its own. So where is that minus 1 coming from? Why is the kinetic term F mu nu squared here also? Yeah, this minus 1 is this minus 1 here. What's special about this? Correct. Therefore, ergo, which one is not independent? Which one? Yes, a naught, a naught, a naught. If you do canonical quantization with a naught, you would get negative probabilities. So it better be that it doesn't propagate. So this is anti-symmetric precisely so that you forbid time derivatives of a naught. Therefore, a naught is constrained. This has a very famous name. You learn in high school. What is the name of this constraint? Gauss's law. Yes. Okay, I was going to start. Okay, very good. Gauss's law. So there are 4 Gauss's laws there. They're the Hamiltonian momentum constraints of GR. So that's the, okay, public service. So now you can tell all your friends when you go to the bar, 10 minus 4 equals 2. And that's why we have 2 polarizations of gravitational waves. Okay, so that's 3 degrees of freedom. Let's see how they appear in the theory of fluctuations. And then we described this ADM, Arnold-Deser-Meissner way of talking about the fluctuations. And the idea is you write the metric as so. This you're not really doing anything, meaning you haven't made any assumption. If you want to see some picture to gain some intuition of this parametrization, so the same Meissner, Thorne, and Wheeler have this phone book, Gravitation, right? This big book that raises many computer screens throughout the world. Sometimes you can lower your computer screen, take the book, and take a look. They have very nice pictures explaining the meaning of this Ni and N. So if you take different time slices, how you glue one time slice onto the other requires knowledge of these fields. So this is called the shift, and this is called the lapse. And this is where the degrees of freedom of the metric are. Okay, so you specify on a 3 slice, sigma some 3 slice, you specify the metric Hij of x and t, and then these, very much like a knot, they are related to G0 mu, if you wish. They don't have dynamics, and then N and Ni are functions of Hij. Okay? So that's how you do, that's how we're going to quantize the theory of the perturbations. So Hij is going to be given by this, a squared t, 1 plus 2 zeta tx delta ij plus gamma ij of tx. And we still have, we can fix the gauge. We have, we can do diffeomorphisms. So this kind of picked some slicing. You build the space-time like stacks of cheese, okay? These American cheese slices. So you stack them, like queijo prato for Brazil. So you stack them one on top of the other, and then you build a space-time, and right, and but you still have diffeomorphisms. You can still pick frames along the time slice, and we're going to use that to set this to be traceless and transverse. Okay? So then this has 2 degrees of freedom, and this has 1 degree of freedom. And through this choice of gauge, you can set the scalar field to be given just by its expectation value. So these slices are slices, so sigma has constant phi. So that's, again, the reason why phi is a clock. So you use phi, the values of phi as it rolls. So it is important that phi has dynamics, right? Because if phi didn't have dynamics, you would have the same value everywhere. So you couldn't use it to slice the space-time. But as it rolls, the value of phi changes, and you can use the different values of phi to build up the space-time, okay? So, in other words, you would not be able to reach this gauge and eat the scalar into the metric if phi did not have dynamics. And we're gonna see that, okay? So this zeta variable does not exist in pure de Sitter space, in which you had a cosmological constant and no dynamics. So this is essential. Okay. So you plug this Hij, there's a whole song and dance now. You take the metric, you plug it in here. Okay, you write that gauge choice for Hij, phi, n and ni will be Lagrange multipliers. You solve for their equations of motion. They are going to be functions of zeta and gamma. Then you solve for them in perturbation theory. You plug it back in the metric. You integrate by parts. And okay, that's a homework problem for you. It's actually a little bit complicated. But I'll tell you the final answer. Because the final answer is very simple. All this work is to land in a very, very simple final answer. There's some nice story about how people first found this final answer. There's a famous workshop in Cambridge in the 80s, around the time that inflation was developed. And people got this wrong in all sorts of ways. And then they figured it out only to discover that people in the Soviet Union had already done it. So Mukhanov and Chibisov had done it, and Starobinsky. So anyway, so this is from the point of view of this spatial slice, this gamma is a tensor, and this zeta is a scalar. So because of rotational symmetry, they don't really mix at quadratic order. So there's no linear mixing term. So there's a quadratic action for zeta. I'm just expanding perturbation theory, okay? Of course, that action has infinitely many vertices in perturbation theory. And I think humans, brave humans, push this maybe to quartic order. It gets incredibly complicated. But the quadratic order is simple. And this is what you get. It's gamma. So there's the quadratic action for the scalar fluctuation, for the gravitational fluctuation. And here's what you get. You get root g m Planck squared epsilon. And g bar mu nu. When I mean g bar, I just mean the background metric. Okay, remember that the background solution is just FRW minus dt squared plus, where A of t is approximately the de Sitter metric, okay? So that's G bar. It's just a free field, and it's massless. To get that coefficient m Planck squared epsilon is really a pain. So, but that's the output of doing this whole procedure. And for the graviton, you get, well, it's not so surprising. If you do it in detail, you get the factors right. You get m Planck squared over 8. G bar mu nu, d bar mu gamma ij, d bar nu gamma ij. So these guys are contracted with just the usual delta ij, okay? So there's no metric, background metric contracting these. So, what is the conclusion? You just have 3 massless scalars in quasi-ds. Great. So we learned how to quantize the massless scalar in ds. So what was the whole fuss about? The fuss was to get the coefficient up front. Remember, these are components of the metric. They are dimensionless. And the point is, if you took the canonically normalized scalar in de Sitter space, it has fluctuations of order Hubble. And now these will have fluctuation of order Hubble divided by some scale. And the whole work was to figure out what the scale is. And the reason we see scalar perturbations and do not see tensor perturbations is because these coefficients are not the same. You see there's an epsilon here. So I delivered my promise. So the scalars do not make sense unless epsilon is non-zero. So you need dynamics. So in order to be able to reach that gauge, it's just like in the Higgs mechanism. You cannot eat, the vector boson cannot have its meal if there's no VEV, okay? So here, the metric cannot eat the scalar unless you start slicing space-time with an expectation value of phi. So, what is this? So, what is the coefficient up front? It's the strong coupling scale for each sector. Okay. So let's see if I. So if I draw energy scales here, there's the Planck scale, and there's this root epsilon. Okay. So this is where, so this is strong coupling for zeta, and this is strong coupling for gamma. And where are we in the experiment? We are experimentalists during inflation. So these are the strong coupling scales. We're claiming we can do perturbation theory, so we better be somewhere down here. So where are we during inflation? What is the scale of the experiment? Yes, the Hubble scale. So what makes this controlled is that there is a parametric separation between the Hubble scale where we sit, this strong coupling scale for the scalar, and this strong coupling scale for gamma. And this M Planck here is, you think, oh, it's Planck suppressed and so on, but this is misleading. So let me, yeah, maybe let's see if you can guess. So what is the scale? What is the scale in which the scalar fluctuations become strongly coupled? What do you think it is? Forget about gravity, forget about M Planck. If you stare at this picture, is there some scale? So what is the scalar perturbation? The scalar perturbation just tells you at each point in space how much of a kick you get that delays or accelerates the history of the scalar. Remember, there is this rolling, and then the zeta at every point gives you a little kick up or down. So when does the theory become strongly coupled? What do you think? What is the scale? M Planck root epsilon, I know, but what is the scale in terms of the scalar? You can look at the Friedman equation and try to figure out what the M Planck root epsilon is, but just intuitively, if you stare at the picture there, what is the scale that springs to mind? No, because it's all related to what's happening here. No, it's not, because so you need to compare two. So this is the perturbation, and this is the history. So, and the scalar is just, remember, it's related to the clock. So even though the potential sets the size of the Hubble scale, the history is determined by the kinetic term, right? Because the history is determined by the rolling. So the scale is phi dot. If the scalar jitters by the same amount of the velocity of the scalar field, so it doesn't make sense to split into background and fluctuation anymore, right? If you're giving kicks of the same order of magnitude, the average velocity that you're moving, does it make sense to talk about average velocity and kick? So that's the strong coupling scale. It's phi dot. Well, phi dot is dimension 2. Anyway, some phi dot, square root of phi dot. Okay, is that clear? I mean, let's, if I write the Friedman equation, we'll see it. Where is it? M Planck squared H dot equals minus phi bar dot squared over 2. Let's, always dangerous to do these manipulations in real time. H squared. So M Planck squared epsilon is phi bar dot squared over 2 H squared. So the strong coupling scale for this, for zeta, which is M Planck root epsilon, is phi bar dot in Hubble units. Okay? So that's it. So it has nothing to do with the Planck scale. It's just the scale at which the scalar field is rolling. But intuitively it should make sense, right? If you give kicks of the same order of magnitude in which you're moving, it doesn't make sense to talk some average speed. So this is the strong, and here, okay, it's the usual story. The graviton is strongly coupled. And so the 2-point function of these fellas here are controlled by these ratios of scales. Because you do the experiments here, this is the strong coupling scale. At strong coupling scale, fluctuations are order 1. And here, the fluctuations are suppressed by the ratio. Okay. So you can just do standard canonical quantization of these scalars, and then we're going to get zeta k1, zeta k2. Now, in the lectures, I've been writing this. In the first lecture, I showed some expectation value in the sky, and you should have asked me, what is this average with respect to? Right? So let me make a little comment about that before I go back to. So here, for us, what we really mean is in the vacuum, you take the operator and compute its 2-point function. Okay? So it's quantum mechanical average in the vacuum. In the sky, we do sort of ensemble average. We have the sky here, and the hypothesis is that every little patch of the sky is an experimental realization of the underlying quantum mechanical process. And I measure here 2-point functions. Here, I measure 2-point functions there, and so on. And the idea, the working hypothesis of cosmology, otherwise you will go home, there's nothing to do, is that ensemble average, zeta, average in the sky equals quantum mechanical average. It would be wonderful to test if this is really true. To really test if this is true, one probably needs some Bell inequality type of experiment, which it's not, well, there is one proposal, maybe I'll mention it in the colloquium, but yeah, it's not in our universe. You can build a toy universe in which you can do some Bell inequality during inflation, but it seems very tricky at the moment to do this sort of test to check whether these fluctuations really have quantum mechanical origin in our universe. Okay. It's an open problem. It would be wonderful if there was a way of testing this. Some property of the correlation functions and so on. The problem is that to do any Bell inequality, you need to measure operators that have a commutator. And So if you take the field and its conjugate momentum, if you remember from, let's go back in the last lecture, when we described the massless scalar, its conformal dimensions were 0 and 3. That means that the scalar, the field might decay as eta to the 0, meaning it freezes at late times, but its conjugate momentum goes like eta cubed, which is like e to the minus 3 ht. So it decays to 0 exponentially fast, so you don't really have access. You have an ultra squeeze state. You just have access to the coordinates. You don't have access to its conjugate momentum. And that's essentially the barrier. Inflation is so good at producing fluctuations that it erases the canonically conjugate variables. Okay? So the only way around it is to try to do the Bell experiment during inflation and try to see the result of the experiment in the sky. So as far as I know, that's the only way to do it. Okay. So now we can compute this, and the classical, so this is just canonical quantization, so it's very easy. Remember that field operator is just given by classical solution A plus its complex conjugate A dagger. So the 2-point function, no, there's no, the scalar is zeta. It's just that you went to a gauge in which the scalar doesn't fluctuate, and then all the 3 degrees of freedom are in the metric. It's just like a massive W boson. The scalar is zeta. That's why it has different strong coupling scale that cares only about the scalar sector. You just went to a gauge where you absorb the scalar perturbation onto the metric. Yeah. Any more questions, by the way? So the 2-point function is just going to be given by, well, this you hit with A dagger, this you hit with A, so it's going to be given by phi classical star. Okay? Yeah, you just have gravitons. That's right. But the things we see in our universe are these ones. So if you throw this away, throw the baby out of the bathwater. So, but if you want to talk about just gravitational waves in some cosmological spacetime or the Sitter-like spacetime, this would be the action. Yeah. Yes, that's right. So this is what Bicep claimed to have observed. Okay. So, right. So this is the 2-point function of your quantum field. And if you remember, the classical solution for a massless scalar was very nice. It was h over root 2k cubed, 1 for a given wave number, 1 plus ik eta e to the minus ik eta. And we assume that these modes cross the horizon, so we're always taking k eta to be very small. So in practice, we're just going to send eta to 0, okay? The correction in k eta is negligible. So what happens is that the 2-point function of a canonically normalized scalar, so this is true if the action has 1. Let me put 1 here. 1 d mu phi squared over 2 minus. So now there's not 1, there's these coefficients. So one way to think about it is that you can define some phi-like variable by absorbing this here. So it's not hard to believe that this correlation function will have this guy in the denominator. Okay? But just to finish the thought here, for a massless scalar, you'd have phi of k1, phi hat, and k2. you will get a delta function from translation invariance, right, from these operators here. So there's really one momentum in the game. You multiply these, because you multiply the mode function by its complex conjugate, you just get mod squared of this. It's 1 plus k eta squared, which we drop the k eta squared term. So you just get 1 from this part. You just get this squared, h squared over 2 k1 cubed. Okay? Another exercise that is not in the problem set, but you can do at home, is that this, if you were to Fourier transform, because the Fourier transform has d3k, and there's a k cubed here, there's a logarithmic singularity. So this two-point function in position space is sort of ill-defined, okay? That's the statement that massless scalars really don't have, strictly speaking, the Sitter invariant vacuum states. But what we like to say is that this is exact scale invariance, okay? So if it was an exactly scale invariant scalar field, you would have 1 over k cubed. We're going to see, if you remember from the first lecture, the zeta variable does not have exact scale invariant two-point function, and we're going to see how to take that into account in a second. But just to finish, so what do you actually get for the two-point function of the gravitons and of the scalars in the end? Okay. So you get zeta k1, zeta k2, be delta. These delta functions appear all the time. So a little bit of notation. The objects without stripped out of the delta function, we call it delta prime. Okay, so that's just a little notation, just not to keep track of these annoying delta functions. So zeta k1, zeta k2 prime is going to be 1 over 2 epsilon h over m Planck squared, which you can write as we saw here, m Planck squared epsilon is phi bar dot squared over 2h squared. So let's see if I can do algebra. 1/2 h squared. I mess this up all the time, so let me be very careful. M Planck squared epsilon is phi bar dot squared divided by 2h squared. So that's h to the 4th. I forgot this, k1 cubed. H to the 4th over phi bar dot squared, 1 over k1 cubed. Great, okay. So this U fits with the data. I mean, so we don't know what these scales are, but at least we know something from the data. We know that this ratio here is of order 10 to the minus 5. Remember that the two-point function goes like 10 to the minus 9. So we learn about the ratio. So we don't learn what h and phi dot are, but we learn about their ratio. Okay? Now, gravitons are exciting because that would give us the Hubble scale in Planck units. So let's see. That will give us 8 h over m Planck squared 1 over k1 cubed. Okay? So if we measure this, which right now we haven't, so figure of merit is, so for sure that scale is higher because we haven't seen gravitational waves from inflation. But you will find often people talking about this object. You take some pivot scale and you look at it doesn't change much with scale, this ratio. So this is called the tensor to scalar ratio. Tensor to scalar ratio. Because it's a ratio, people call it R, and R, for slow roll inflation, you can divide these two things. It's a proxy of this slow roll parameter epsilon. It's epsilon, 16 epsilon. And we know right now that it's at least less than 0.05, okay? This is from observations. The facts that we haven't seen, these gravitational waves tell us that, but that's okay, you know? So R less than 10 to the minus 2 means that this other scale here is maybe 10 to the minus 6 or 10 to the... Of course, it can be very, 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 very far away. But, well, maybe I'll make a plausibility argument that it could be around the corner, okay? The future is good. Maybe bright is an exaggeration, but the future is good. In particular, there is an experiment spearheaded by the Japanese called Lightbird, satellite experiment, that is going to actively hunt for this signal. And, well, hopefully we see something. The worst case scenario is R will be less than, depending on who you ask, big number 10 to the minus 4, maybe conservatively 10 to the minus 3. So it's going to improve on this by an order of magnitude. This is the good news. The bad news is that if they don't see anything, it's going to be very, very, very hard to see gravitational waves. Because, anyway, it's a bit too fino, but the gravitational waves, we see them indirectly. So, so when these scalar waves, they are stretched, okay? So they're stretched and they're frozen at the end of inflation. And then as the universe enters this hot phase, the scalar waves just produce potential wells. And then stuff falls in clusters, okay? Now if a gravitational wave enters the horizon, what does it do? It's a tidal wave, right? It's spin 2. So stuff doesn't fall in. Stuff just sloshes around it. So it doesn't build structure. It doesn't cluster up structure, it just aligns it, okay? So what it does to the CMB photons is it polarizes them in a special way. So you would, if you look at the CMB photons as little arrows, they are linearly polarized because they scatter, anyway, long story. So it's polarized. So if you had microwave eyes and you had these fancy Ray bands with polarimeters and you looked at the CMB, you'd see that the power changes as you tilt your head up and down, okay? And these swirling patterns of polarization know about the presence of these primordial gravitational waves. Because unfortunately, they don't cluster. So they don't leave a massive imprint in the data, but when they enter the horizon, they make the photons polarize in a specific way. So that's how you look for them. It's not so easy to look for them in galaxies. There is some proposal, I can tell you, offline. But you know, there's only one CMB, only one universe to see, only one CMB to observe, and the CMB has only so many pixels. We call this sad thing cosmic variance. There's only one universe to observe, only a certain number of pixels, so the best experiment you can do can only tell you so much about the universe. And this is very close to cosmic variance limited, this measurement, meaning you'd have to find a new way of measuring. It wouldn't be only through the CMB, okay? If you detect, though, if you detect, well, if you detect these, oh, first of all, let me emphasize that this is the exact same physics of Schwinger pair production, of Hawking radiation, of... actually, the pioneer of this was Parker, Who ever heard about Parker? Okay, well, good, some people. Parker deserves a lot more credit. So he was the first one to notice that cosmological evolution produces particles. So in some sense, the physics of Hawking radiation, Schwinger pair production, has been observed in these scalar fluctuations if you buy this framework of inflation. Okay? Now, so we have seen this, and now if we detect gravitational waves, despite the fact that it's super cool, you're seeing, you know, the shearing of the early universe reaching our detectors. It's literally the universe contorting and stretching itself. So if we detect these primordial gravitational waves then H is pinned because we know what G Newton is. There is nowhere to hide. We know what the Planck scale is. Then H is of order 10 to the 13 GeV. I mean, if you're not a particle physicist, maybe this number doesn't mean much to you. That's 10 billion times the energy scale of the LHC. So people now talk about in 50 years from now going a factor of 10 above the LHC. This is nature giving us a detector at 10 billion times the LHC. Unfortunately, the experiment was run just once. So it's an experiment of low luminosity. But it's a very high energy scale, okay? So we should try to exploit it. Before I go to trying to exploit this, let me make one more comment, which is about the scale dependence. So if I look at these formulas here, it looks scale invariant because there's 1 over k1 cubed here. But the catch is that h and phi dots are mild functions of k, right? It's really h of k and phi bar dot of k. Why? Because all the fun for a mode happens when it crosses the horizon. Right? So a given mode of wave number k cares, so wave number k cares about eta star 1 over k. So you should evaluate h at a time eta equals 1 over k. Okay? So, I mean, intuitively, if you draw the picture of the potential, then at different times, the scalar field is at different parts, exploring different parts of the potential, so the potential energy changes. And as it's rolling, its velocity also changes. So there's a little exercise at evaluating this, comparing to some pivot scale, evaluating this at slightly different times, taking this into account. Okay? This is an exercise. It's a fun exercise. You don't need to do anything fancy. It's just Taylor series and using the Friedman equation. And you will find that because of this mild scale dependence, you find that you can just set this at some pivot scale k star and write k to the ns minus 1. Okay? And here there will be evaluated at some pivot scale k star, k over k star, of course. And here would be k over k star. By this time, people were more sensible and they wrote nt. So for the scalars, it's ns minus 1, and for the tensors, nt. So nt is small and ns is close to 1. Okay? So it's not my fault. So ns minus 1 is given minus 2 epsilon minus eta. Remember, okay, let me write the formulas. So these 2 epsilon terms come from the fact that h is time dependent. Well, it makes sense, right? Because the time derivative of h, you just Taylor expand. H equals h at some pivot scale plus some linear term that goes like h dot. and h dot goes like h dot over h squared is epsilon. That's why epsilon appears here in both terms. The scalar has a second term, which comes from the fact that there's phi dot. Then you use the Friedman equation, and you write the time derivative of phi dot, blah, 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 and you get this second guy. Remember that eta is epsilon dot over epsilon h, okay? So this has been measured. This Planck famously measured with, I don't know, 10 sigma accuracy. So this is order 10 to the minus 2. Now let's make the case to the funding agency that we should go to the sky and measure gravitational waves. How do you make that case? We have measured this, 10 to the minus 2. The tensors are of order epsilon. And this is affected by epsilon and eta. And slow roll parameters are small, naturalness, same order of magnitude. So unless there's some enormous cancellation and this only comes from eta and epsilon for some reason is 10 to the minus 5 or 10 to the minus 4, then there is a plausibility argument that tensors are around the corner. Okay? And if tensors are around the corner, then h is of order 10 to the 13 GeV. So that should make you wake up in the morning and say, I want to work on inflation, because there is a possibility that inflation is the highest energy density event in the history of nature. Okay? Yeah, if there's a bound from, if there's a minimum, yeah, it can be insanely low. It can be 10 to the minus 50. Because you can, the only thing you really need is you need inflation to end. You need enough energy density from this inflaton to heat up the universe and do Big Bang nucleosynthesis and so on. So remember that it has some energy, and then when we roll down here, it needs to dump all of its energy into the plasma, heat up the plasma to form nuclei. Okay? But you do Big Bang nucleosynthesis comparable to these scales at very low energy. So if you plug that in and you run the numbers, you'll find that you can do inflation at tiny, tiny Hubble, in which case h over m Planck will be 10 to the minus 60. If you do inflation at tiny, tiny, tiny Hubble, then this issue of how you start inflation becomes infinitely worse. Okay, so that's yeah. So that's the lower bound. It could be that it's 10 to the minus 60, and we'll never see this. But this is, I just made my argument as the lawyer for a slow roll inflation. As the funding agency, you can say, but what about the BBN bound? Your choice. Okay. No, because we have only seen scalars. The only consequence of this is that we'll never see tensors. And then we need to understand inflation by focusing on the scalar sector only. The scalars can have higher point functions, you have interesting higher point functions. It just means that anything that involves a tensor mode is beyond reach. There are two sectors. The plausibility argument is that they're not so much scale separated, but it can be that the one is like zillions of orders of magnitude away from the other, and then you'll never see the tensors. They're ultra suppressed, and then you should focus on the scalars. That's a completely fine attitude. Okay? Any more questions? Yeah.
You talk about the Bunch-Davis vacuum, okay. And since we don't have many bounds on the tensorial modes, we could, for example, relax this statement for the tensorial modes when we quantize them? Like, I don't know, being something like the scalar modes being Bunch-Davis traditionally, or the tensor modes be something different, some linear combination of the Bogolubov coefficients.
I think at the level of the two-point function, it's going to be all scrambled into these coefficients, right? If this coefficient is h over m Planck, it's a modeling interpretation. If you do alpha vacua and so on, I think you'll still see a power law like this, but then you would say, I didn't measure h over m Planck. I measured some mixing of h, m Planck, and the alpha vacuum parameter, but you're still looking for this number. I think the distinction will become important when you go to other observables beyond 2 points.
Okay, thank you.
Okay, so let's move on. So I spend a lot of time talking about this because this is what we observe, okay? So this is the part of inflation that probably everyone agrees is very reasonable and matches our universe, makes inflation a compelling framework. There are the fact that the momenta, the conjugate momenta are suppressed, also gives lots of striking phenomenological consequences that predict some pattern in the polarization of photons, that you can really prove that these fluctuations were there at the Big Bang. You can't fiddle, maybe there's some late time physics that kicks in and explains the CMB. There are some striking predictions of inflation that you cannot mimic with late time physics. So we know that these perturbations need to be there at the hot Big Bang. So this is kind of a neat story that I'm not going to have time to review for you. So I'm going to move on and enter the speculative part, which is the fun part of the lecture. So I did my duty of educating you on the part that everyone agrees is solid and connects to observations and so on. And now I'm going to talk about the next thing, which is related to going beyond the two-point function. So this is about primordial non-Gaussianity. So primordial non-Gaussianity is a very fancy name for interactions. Okay. So a free field is Gaussian, right? You only need the quadratic action. Everything is determined by the two-point function. The four-point function comes from Wick's theorem. The three-point function is 0. So if you have non-Gaussianity, odd correlation functions or connected endpoint functions, then that tells you that the model is interacting. So what's the story we tell? So here's the end of inflation. And we spent the last 2.5 lectures talking about this diagram here, okay? We talked about it for the scalar, and we talked about this one for the graviton that we would love to measure, but we don't know if we'll be able to. We're trying. And what about 3 points or 4 points? I'm mostly going to focus on 3 and 4 points because the typical size of a fluctuation is 10 to the minus 5. So every time you add a point, you pay a price of 10 to the minus 5. There's only one universe to observe, so it becomes more and more unlikely that we'll have the statistical power to go much further. But, you know, that never stopped a theorist. And you can keep going and study tail effects in the PDF. You can study endpoint functions. There's a fascinating story of how to think about quantum fields in curved space here. Okay? So, what is the story about that you could tell in these cases? So, how do you open up this blob? At 2 points, it's pretty boring. In some sense, it's just free field propagation. There are these quirky things about quantum fields in curved space and so on. But in the end, it's about doing canonical quantization the right way. At 3 points, what happens in the blob? So there are a few things you could do. I talked about it before. You can have self-interactions. You can have exchanges with new states. So you can see non-Gaussianity as a particle detector, okay? Because say that this pink particle is massive, okay, heavy in Hubble units. So we saw yesterday that its two-point function decays. It redshifts away with time, but it can propagate a few Hubble volumes and decay into the inflaton, in which case it's going to leave an imprint in the three-point function. So you can use the three-point function as a particle detector. Okay. You could say, why not the two-point function? Well, because the two-point function is so pinned by symmetry that you'll never be able to tell. So you could have asked, what about this? I take two-point function and I do something like this, okay? What about this? The problem is that this and this, or the sum, always gives you the same answer. The data of the pink particle just appears in the coefficient. So you're just moving around in interpretation space. You're not really seeing anything different. You interpret the same result in different ways. You say, I saw scalar perturbations. No, I saw scalar perturbations exchanging zillions of loops of other particles and so on. And okay, whatever. You're just seeing the same signal. Okay? So you want striking prediction of a new signal. So that's the reason why this is not, it might be there, but it's hard to disentangle from free propagation. Okay? That's because of symmetry. So this is like particle detector. Maybe there are other things. You could have some strongly coupled sector. Some strongly coupled sector. And then you would have an interesting two-point function. Let me draw a banana here for two-point function. Say that there is some QCD-like sector during inflation, and then you couple to a current in this QCD sector. You think, I'm just going to produce some particles, and then it just sprays, produces partons and all sorts of crazy stuff. And then you have an interesting two-point function here. How would you be able to tell that there's some strongly coupled sector? How do you measure the spectral density of this two-point function? Okay, so maybe some strongly coupled. Oops, there's the yellow. Maybe some strongly coupled. So, yeah, I like, let me go on a little rant here. So, you should think of these zeta and gamma as some gauge boson. That it's like a W boson. Even though it's the Higgs mechanism, there's no Higgs. It's like we're talking about theory of W bosons here because we just absorb the scalar fluctuation. And these fluctuations, forget about now potential, scalar rolling down a hill. Forget about all of that. That just builds a God-given background to you, okay? You take this background and you study scalar fluctuations on top of it. And you can build a very good effective field theory of these fluctuations. It's called the EFT of inflation. And it's essentially the nonlinear sigma model on some curved background. Okay? So there's the nonlinear sigma model for zeta and gamma. Of course, the nonlinear sigma model has a strong coupling scale. Right? What's the strong coupling scale of the nonlinear sigma model here? No, not M Planck. It's on the board. There are two scales, and I said it's not one, so what is the strong coupling scale? It's this one, and we call it, generically we call it F pi. Okay? Does anyone know where this comes from? Yes, pions. It's the pion decay constant. Okay. So if you probe energy scales at which you're probing the pion decay rate energy scale, it doesn't make sense to talk about pions anymore. The pions are melting. So this is the strong coupling scale. In our case, it's m Planck root epsilon, or phi dot in Hubble units. And the question is, what UV completes it, right? So what's the UV completion? Does this problem ring a bell? If not, you should stop doing holography a little bit and study particle physics. This is the history of particle physics. Huh? There's pions, there's mesons, everything is the nonlinear sigma model in nature at low energies. And nature knows how to UV complete in two ways, essentially. What are the two ways that nature knows how to UV complete? Well, let's see. Let's see. I'll give you a hint, there are no vowels here, so let's start with the consonants. So, very good. Now, the other one? Q. The answer is on the board, by the way. What is this? Linear sigma model. What is this called in the standard model? What is this called in the standard model? Come on. Higgs, the Higgs. So that's it. So there are two ways that you UV complete the nonlinear sigma model in nature. The electroweak way is the linear sigma model, it's the Higgs. Or the QCD way, like particles, pions are composites. Okay? So this is called, weakly coupled UV completion, and this is called strongly coupled UV completion. Okay? Weak coupling, strong coupling. And these are, this would be, like in inflation, we have these pions, and we just described the linear sigma model UV completion. In inflation, the linear sigma model is called slow roll inflation. Slow roll inflation. Okay? Because we just, you see, this is the theory. It's just a scalar field rolling down a potential. It's just like the Higgs. Okay, the details of the potential differ and blah, 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 but it's the Higgs. And then when you expand around the solution and you write the effective action for the fluctuations, it becomes the nonlinear sigma model. That becomes strongly coupled at the scale in which the fluctuations are of the order of the velocity of the scalar, and UV completed with the inflaton. Okay? But there can be other ways, and this is just to say that we don't have really an inflationary, or at least many benchmark examples of an inflationary analog of this. So this is why I drew this blob, that it would be interesting to explore this scenario. Okay.
Can I make you a question?
Yeah.
When you open up the blob, you said, okay, I have some options. The options that you have come also from a sublink expansion of the on-shell action you just erased. Like, am I thinking that the rules are set from that effective action, or I'm
no, the effective action is a bit like a pion Lagrangian with different rules. So that action will definitely break down at the f pi scale. The question is, how do you keep climbing up? So there's this d mu zeta squared, and then there's going to be some zeta dot cubed plus ta ta ta. And then at this f pi scale, there's some f pi squared here. And the f pi scale, this whole thing breaks. And then how do you uplift to a bigger theory? And we just described that one way of doing it is to start from this theory here. And this theory is well defined above f pi. But this is one way. There could be others. And we would like to know how to map different UV completions, and maybe it tells different stories about the coefficients here or other states that appear in this EFT and so on.
Okay, so let me make my question simpler. In the second graph that you have called particle detection, you have a vertex that turns a graviton or a massless tensor into a massless scalar. But that wasn't part of your effective action. So which...
This is not a tensor, it's any other particle. So there's some sigma particles that help to UV complete. And this is some operator that, yeah, so just like, let's think of particle physics, right? We have fermions, we smash them together, we learn about W bosons. So that's the picture here. I have these scalars, the nonlinear sigma model, maybe they exchange some W bosons and we learn how to UV complete.
Thank you very much.
Yeah.
Can you talk a little bit more about how the EFT of inflation is constructed? I mean, is it like a bottom-up EFT? Is it a top-down that you start from the Lagrangian?
No, it's like the standard way that you build nonlinear sigma models. There's some symmetry breaking pattern, and you do some beefed up version of CCWZ, Cullen-Coleman-West-Zumino. So the idea is that the cosmology gives you a foliation of space-time. So then you just build operators that are consistent with this foliation. So for example, G00, it is spatial GIF invariant, so it's a good operator in this theory. So you just say that this is allowed to appear in the EFT. So how do you UV complete this operator? What is the UV version of this operator within single field slow roll inflation? It just be G mu nu, D mu phi, D nu phi. That's the easiest way of understanding the EFT of inflation. You take anything you can build out of single field inflation, and then you put phi on the background. Let's see. If you put phi on the background, this is time dependent, so only the zero component survives, you get G00. Okay, you would say, now I have phi bar dot squared. But the point of the EFT is to say this is just a function of time. I just erase this, and the EFT only knows about this operator. And the function of time is a free parameter. Then you can decide how you UV complete it. So any operator in the EFT of inflation is like that. So there will be, I don't know, G00 squared. This is a famous operator. Because what is it? It's just d mu phi squared. So it's dimension 8, right? Dimension 8, so you need to divide by some strong coupling scale to the 4th. And so if you put things on the background, you would write G00 squared, phi bar dot to the 4th over lambda to the 4th. And in standard single field slow roll inflation, this is very small. So you just said, I don't care about this operator. In the EFT of inflation, you just say this is a function of time. And then this can be an interesting operator. So what does this operator do, for example? It changes the dispersion relation of the inflaton, right? Because if you plug it maybe twice on the background, what do you get? You get d mu phi squared. You get d naught phi squared, phi bar dot squared over lambda to the 4th. So that creates a mismatch in the kinetic term and changes the speed of sound of the inflaton, right? And this is usually a tiny change in slow roll inflation, so you don't care. But if you make this operator big, you generate a big change in the speed of sound. And what's the consequence? You beef up the interactions because the same operator also controls this guy, d mu phi squared, phi d naught phi bar dot over lambda to the 4. Now I put one guy on the background and 3 perturbations. So this cubic vertex is now enhanced. So the EFT of inflation teaches you these things, that if you make the speed of sound very small by changing this operator, it makes non-Gaussianity very large. So it correlates these things. So that's what the EFT of inflation buys for you. But it's very simple. You just take your favorite model of single field inflation, add all sorts of irrelevant operators, evaluate them on the phi bar of t that builds the foliation, and then forget about anything that depends on phi bar dot. Just promote it to a coefficient of time. And then you're going to build all the operators in the EFT of inflation. Okay? So that's it. Yeah. It's this. Yes. Yeah, it is true that most likely you should see this first. Now there's a little bit of a catch that these guys, they leave features. So you could hunt for the features. Maybe this, it might be a big signal, but it's sort of boring. It's featureless. And these guys, they leave features because you pick up a phase as this guy traverses. So I would say that the general attitude is that you should first see this to then look for these guys. In which case, I can quote the bounds on these. The problem is that with the CMB, we're almost saturated on this type of searches. And large-scale structure is not going to be very good at searching for this. Now there is something else, which is you can make this mediator particle very light in Hubble units, in which case large-scale structure will help and will improve the bounds by maybe an order of magnitude. So that's the most exciting direction in terms of detection. So I probably need to explain tomorrow why. So if I have a very light mediator, I can couple things over a wide range of scales. Well, here I can't. So that's why with large-scale structure I can do better than what we have right now. So tailing on Alan's question, even if you don't do any, sorry, yeah.
Professor, just follow-up question. It was not clear to me why LSS wouldn't be good to probe that.
Why what?
Why large-scale structure?
Because this type of signal is degenerate with late time evolution of galaxies. Okay. So it's hard. I mean, you see the correlation, but you don't know how to tell what came from inflation, what came from late time physics. So that's the big challenge. If you, the nice analogy is that the CMB is like QED, and the large-scale structures like QCD jets. So there's all sorts of, well, people call astrophysics. There's all sort of junk that you need to get rid of to see the primordial stuff. So that's the problem.
And what would be the difference for the second case that you said that we could
Yeah, for the second case, because you couple very long scales with very short scales, it leaves an imprint that from causality, the fact that large-scale structures formed over some finite range of time, you can't generate this signal. So this guy here couples very long scale. It's the way that it appears in galaxies that it seems that galaxies are breaking the equivalence principle. That's the word that people usually say. But of course they're not. It's just that they're being modulated by some background wave. And then you would see that there's this modulation. It comes from this type of signal.
Thanks.
Yeah. So, yeah, just I have, how many minutes do I have? 10? Okay. Just tailing on Alan's question. So, without doing any computation, now we have great intuition about inflation. We're all specialists. And we can guess what the signal looks like before getting our hands dirty. So this self-interaction, I guess it should have done like this. It's a function of now the three momenta, K1, K2, and K3, but it's really a function of the three momenta, K1, K2, and K3. The absolute values because of rotational invariance, and a little bit more of the translation, because you could have said the dot products appear, but in the end, anyway, yes, you're right. So it depends only on the sizes of the triangle, and so you have a function of a triangle. So physicists classify triangles in two forms. They're equilateral or they are squeezed. That's what we learn in high school, right? That's the physicist way of talking about triangles. This escalene, isosceles stuff, who cares? Because there's equilateral and non-equilateral. So the difference is that there is a hierarchy of scales between the momenta. So here is K1 order K2 order K3, and here it's K1 is much less than K2 order K3. Okay? So this is called squeezed, and this is called equilateral. So where do you think there will be, so of course this is a function of any momenta, so I can go to this configuration. Oh, first of all, if I rescale, if I blow up, you could say, oh, I can rescale the triangle. But because of scaling invariance, remember that the two-point function went like the two-point function phi went as 1 over k cubed. So if I rescale, I just rescale k, I get essentially the same result up to some rescaling. So the same thing happens here. If I rescale the momenta, I get the same result up to some rescaling. So it's not very interesting. It's because of this. Remember, I was telling you yesterday, in the sitter, it's very easy to argue for a bigger lab. If I do the experiment tomorrow, I want to get the same result, I need a bigger lab. So it's just this scaling symmetry. So what really matters is the shape of the triangle, not the overall size. So for this type of diagram, where do you think there will be more signal? In this configuration or in this configuration? Who thinks it's, well, I know that there are people that know the answer, but let's, Brazil, it's mandatory vote. You have to vote. There's no way around it. You have to, otherwise you have to pay a fine. So, who thinks that there's more signal in equilateral? Raise your hands. Okay, who thinks there's more signal? You know, there's a fine, just FYI. Who thinks there's more signal in squeezed? Raise your hands. Okay, everyone else gets a fine, so come ask me for the fine later. But actually, you all lost the election, so it's equilateral that has more signal than squeezed. Why? There's only one instant in which interesting things happen. So these three modes are generated at the same time. So when these three waves are generated at the same time, they are stretched by the same amount by inflation. So therefore, you cannot generate a hierarchy. So if there was a lot of signal here, it means that on the diagram, you generate some hierarchy. There is a strong interaction at different scales. Remember that everything happens, so for every momentum, you associate a time scale. Horizon crossing, k eta star, order 1. When it's equilateral, there's a single time scale, k1, k2, k3. Any of them, eta star, order 1. So there's only one eta star here, eta star, order 1 over k1. So it produces equilateral type non-Gaussianity. of course, quantum mechanically, sum over histories, blah, blah, blah. So you generate signal at every kinematics, but it's much bigger in the equilateral shape than in the squeeze shape. So, and for this reason, we call this, you guessed, equilateral non-Gaussianity. Your guessing is going to go wrong in a second. So this is called equilateral non-Gaussianity. Now let's try to engineer the opposite. I still keep... let's try to engineer the opposite. So how do I make the signal peak around the squeeze configuration compared to the equilateral configuration? So now I need 2 times, and I need the 2 times to be separated. Okay, so I draw a picture. Here's my yellow. Here it is. Now I want the squeeze configuration. Remember, one of the wave numbers is much smaller than the others, so one thing needs to be happening much earlier. So that's the, and then these 2, something needs to be happening later. And this is the type of signal that is going to generate non-Gaussianity of this type, right? There's K1, K2, K3. This is of order 1 over K2. And this is of order 1 over K1. And if you draw this diagram and say this is the signal, then you should return your diploma as physicist. So then you need to fill in the figure with something. So what do you put it here? You put a mediator. Now you want the signal to be big. So if you want the signal to be big, you want this mediator to have a big 2-point function. And what's the price you pay if you make this mediator propagate a long distance? What's the price you pay? No, what's the price? The price you pay. The mediator has fixed mass. I think you kind of you jumped ahead. You said the right answer, but what's the price you pay? Redshift, no? So you need to beat redshift. If you put a mediator that is very massive, it can't take a message a very long time. So if you want this to be very big, this coupling, the mediator better be very light. So in the limit where the mediator is massless, then you have maximal coupling between K1 and K2, K3. So what is this called? This type of non-Gaussianity. Reasonable people would have guessed squeeze non-Gaussianity, but we're not talking about reasonable people, we're talking about physicists, so this is called local non-Gaussianity. It's the most non-local process you can have during inflation, but it's called local non-Gaussianity. And okay, I'll try to save face of the name. The reason is because from the point of view of this reheating surface, it looks like you took a Gaussian field and did some local Taylor expansion of a Gaussian field. So you should think of this as maybe some Gaussian field squared, okay? And this is some Gaussian field. So the story you tell is that, you know, the density perturbation we see is really a Gaussian field that we sample with some Taylor approximation, Gaussian squared. So it's local. So it's local from the point of view of reheating. So it's that fixed time. Zeta Gaussian of x, zeta Gaussian squared of x. And lo and behold, if you plug these ansatz into a 3-point function, zeta of x. If you plug these ansatz, then you see that there will be a term that is linear in FNL that involves a 4-point function of this Gaussian field, right? Zeta Gaussian, zeta Gaussian, zeta Gaussian squared, and you use Wick's theorem, okay? So that's where it is. I mean, this story, you can there are models of inflation which this story makes sense. They don't really fit into this slow roll or single field or quasi-single field type of scenario. They're a little bit more, they have more bells and whistles. And so if you want this type of mediator, then it's the most non-local type of non-Gaussianity. It's squeeze type of non-Gaussianity, okay? Of course, now you can do everything in between. You can put massive particles, you can put different two-point functions, and the shape will differ in detail. Okay. So what we're going to do next time, tomorrow, I'm not here, but Thursday I'm back for 2 lectures. So on Thursday, I'm going to give you a flavor of how we compute these non-Gaussianities, and then we'll see. So I'm going to keep going as a responsible lecturer, but I kind of want to do something fun and a bit crazy in the end. So I might do 1 lecture following the sort of logical way, and then I'll just jump and do something more, we'll see. Or I'll just be boring and do everything by the textbook and keep going. We'll see how it goes, okay? But my plan next time is to give you some flavor of how we compute these non-Gaussianities by various methods, either by Feynman diagrams or by something called the wave function of the universe, or these bootstrap type of methods. And then we'll see where we go, okay? And yeah, so maybe I'll mention these experimental bounds and so on at the beginning of the lecture tomorrow, because it requires some work to define the observable properly. So I'll stop here.
Okay, question?
Thanks for the lecture, Professor. What I'm curious about is that we have observational results on the CMB for inflation, etc.
Yes.
But there is still the rewriting phase. Do we know of any idea of some observation, something on large-scale structure to probe the rewriting period?
I think the short answer is no. You could imagine that there are scenarios of reheating that maybe leave some topological defects, some relics that survive thermalization, and you could look for those. One thing that reheating does is it changes a bit the shape of the bare inflationary potential. So it kind of renormalizes. It's a bit like a Coleman-Weinberg, for example. So it changes the number of E-folds. So, I mean, if you really pinned the model of inflation and you really wanted to trust the number of E-folds, maybe the number of E-folds of inflation that you gets changed depending on the reheating history. But that's very indirect. I think you wanted something more direct probe of reheating. And reheating heats up the universe, and thermal systems famously erase initial conditions, right? So I think it's very challenging. I don't know of a direct way of testing, but maybe I'm not the most qualified person to answer this question.
Okay, thanks.
Okay, more questions?
We are hungry.
Sorry, I can understand the comment about in the equilateral no-Gaussianities, the one-time characteristic. For each frequencies, you have a time characteristic, or you say something like they are one time.
Well, of course, if you blow up the equilateral triangle or shrink, then there are different times, right? But the point is that if you try to probe this configuration, there is a tension because this mode wants to be produced at some earlier time compared to these. So there will be some interference between the history in which this mold is produced first and these molds are produced later. There'll be some interference between the two diagrams, but interference is destructive. It's going to make this signal be weak compared to this. So that's the... Just if you stare at the classical diagram, it seems that it's controlled by a single scale. That's why you should expect more signal here. But there's support in all kinematics because it's quantum mechanics, right?
Okay, but they are not an wavelength with preferred.
No. The idea is that the scales that we probe, because they experience roughly the same Hubble constant, you should get more or less the same signal at all scales. There will be similar effects to the... Remember that the 2-point function of the scalars had this h over phi dot, h squared over phi dot squared. But then every mold experiences slightly different values of the background solution. So the same thing will happen here. So these non-Gaussianities are going to have equilateral shape, and maybe the bigger triangle, because it probes earlier times, experiences different Hubble. So the same story will appear here. But this is a subleading effect. Right? So the leading effect is just this, that they are more or less the same signal. But then in detail, if you could really measure the scale dependence of the non-Gaussianity, then you would be sensitive to these effects. Yeah.
Okay.
Okay, well, let's thank Guy again.
Thank you.